Welcome to The Explainer. Today, we're talking about something that's probably on your mind if you're interviewing for a data role, how to absolutely ace those questions on Delta tables in Microsoft Fabric. We're going to break down everything you need to know.
So, if you're a recent data science or engineering grad, you know the technical interview is, well, it's the biggest hurdle, right? And when you're talking about Fabric, I can almost guarantee you're going to get questions about delta tables. Why? Because it's literally the foundation of everything you'll be doing. We're going to cover all the key concepts you'll be asked about, the stuff that really matters. And the best part? To make sure this all really sinks in, my colleague Grudgeon is going to walk you through a hands-on demo in a notebook. So definitely stick around for that.
All right, let's get into it. The interview basics. We'll start with a question you'll probably get right off the bat. So, the big question, what exactly is a delta table? Well, think of it this way. At its core, it's basically an upgraded, superpowered version of the data files you might already know, like Parquet. But, and this is the key part, it comes with all these critical data warehouse features built right in. Things like ACID transactions, which is just a fancy way of saying your data is safe and won't get corrupted. It's the best of both worlds, really. So why is this the standard in Fabric? I mean, why did they pick Delta? It's all about providing this one single source of truth that's super reliable and fast. It doesn't matter if you're using Power BI or Spark or any other tool in Fabric, it just works. And honestly, the best part? Fabric just handles all of this for you, behind the scenes. You get all this power without having to do any extra work. It's pretty awesome. Okay, next up, the core operations, or what I like to call the CRUD test. This is where the interviewer wants to see some code. They're going to ask, how would you actually do this? All right, let's start with the easy one, adding new data. To insert new rows without messing with the data that's already there, you're going to use write mode append. Simple as that. Now for updates, here, you'll use the update method. You just need to tell it two things, a condition to find the right rows, and then, of course, the new values you want to set. It's super straightforward. And deleting records? Well, it's pretty much the same deal. You use the .delete method, give it a condition, kind of like a where clause, and poof, the records are gone. Okay, now for the real powerhouse, the merge statement. This is your secret weapon for handling what we call upsert logic. You know, when you need to update records that already exist but insert the ones that are new. Merge does both of those things in one single safe operation. This is a huge deal, and trust me, interviewers love to ask about it. All right, let's talk about managing your table's schema. This is a big one. It shows you're thinking about data integrity and how things might change over time. So, by default, Delta tables are pretty strict. They use what's called schema enforcement. Think of it as a bouncer at a club. If your data doesn't match the list, the schema, it's not getting in. This is great for safety. But what if your data source adds a new column? That's where schema evolution comes in. You can flip a switch and tell the table, hey, be flexible. If a new column shows up, just add it. It's all about that trade-off between being rigid and safe or flexible and adaptive. Okay, so that leads to the obvious follow-up question you're going to get. How do you actually do that? How do you enable it? It's actually super simple. You just add one little option to your write command, merge schema, set to true. That's it. That one line tells Spark to allow the table schema to evolve and accept the new columns. Easy peasy. Awesome. So, now we're getting to the stuff that really makes you stand out. Let's talk about optimizing for peak performance. Any good candidate knows how to work with data. Great candidates know how to make it fast. First up, partitioning. Imagine you have a giant filing cabinet. Instead of throwing all your files in one drawer, you label the drawers by year. That's partitioning. You're physically dividing your table into smaller chunks based on a column's value, like a date or a region. Why does this matter? Because it lets Spark skip reading tons of data it doesn't need, which makes your queries way, way faster. So let's say you do that. You partition your data by year. And then you run a query like this, asking for something where the year is 2025. Well, what happens is that Spark is smart. It knows it doesn't have to scan the entire table. Instead, it goes directly to the partitions it means and completely ignores the rest. So maybe you have hundreds of partitions, but for this query, it only has to read a tiny number, let's say just 4. That's partition pruning in action, and it is a massive, massive performance booster. And then there's VORDER. This is a special trick that Fabric does when it writes the data. It's an optimization to the Parquet files themselves that makes reading them lightning fast, especially for tools like Power BI and SQL.
You don't have to do anything, but you should absolutely know what it is and mention it in an interview. It's a big Fabric feature. Okay, time for some advanced features. Knowing these will really show you've done your homework. You don't need to be a deep expert here, but you should be aware of a few things. First, time travel. Yep, you can literally query a table as it looked yesterday or last week. Super cool. Then, know the difference between managed and external tables. It's all about what happens to the actual data files when you drop the table. Also, be ready to talk about maintenance commands like optimize and vacuum. And finally, here's a classic gotcha question. What's the difference between save and save as table? The short answer is save as table is for your default location, while save gives you the flexibility to write anywhere. So that's the theory. And honestly, getting a good handle on all these concepts, from the basics all the way to the advanced stuff, is what will set you apart. So let's wrap this up with your interview cheat sheet. Number 1, know your CRUD syntax cold. Append, update, delete, and merge. 2, be able to explain schema enforcement versus evolution and why you choose one over the other. 3, talk about performance, mention partitioning and view order. And 4, know the little details, like time travel and the difference between save methods. You master these 4 things, you're going to be in fantastic shape. All right, enough talk. To see how all this actually works in a real notebook, it's time to hand things over. Rajan, it is showtime. You may now proceed with your demo.
Hi guys. Okay, so let's see the demo, how this thing works. So right now I have created a workspace Carolina, and I have created a Lakehouse Carolina. And inside that I have uploaded these external products. I have uploaded this product.csv. So from this file we are going to create the delta tables, and we are also going to create managed and unmanaged delta tables. So this one is managed here, this one is external. So we will see how to create this, and then we will work with the IoT device data, how to capture and display it. Let's see this. So first of all, in this cell we have created, like, we are defining the schema and we are reading the CSV file with this command .format. And then so once we read this file, we can see the data is in the data frame. We are displaying it. Then we are creating delta tables. One is managed, where we are not giving any path here. Here we are giving, in the second one we are giving path. Save as table, external products, this is the name, this is the path. The whole path we have given here. Okay, in the files and external products. So this is where the data should reside. You will see there is a slight thing we need to see. So once that we execute those things, and if we go and see the managed, like if we say describe, this is the SQL magic commands, so we can write the SQL inside the notebook. So when we say describe this table managed, we have to see here the path. See, the location is inside the tables DBO. This is the location. Same way, if you see for the external table, the location is actually, it's in the file, but for some reason it's showing here tables, but actual data we will see later. Its actual data is in the files actually. So and when we drop the managed and external tables, the difference here is that the managed table, the Fabric is managing both the data and metadata. So for managed products table, data table, when we say delete, we delete both data and metadata. For external products, we don't delete both because we don't even have the external data. It's stored somewhere in AWS, GCP, anywhere. So in that case, we will be deleting only the metadata. So that's the difference. So the data doesn't get deleted. So in here, when we say create table products using delta location files external products. So this command was giving some error. So then I have given the full path below here. So this is the location where it's residing here. So this command works fine. The way I did it is created from external products, so we went to external products and copied the Azure Blob file storage path. So I copied the whole path and pasted it here. So then once we create table using this delta, we can query it here. So this is not much new here. So the good thing about these data tables is that we can see the different versions of the table data. So here we will see that we update the products table, we reduce the sales price by 10%. So the list price, we are saying list price star 0.9 for the mountain bikes. So once we run this command, when we say describe history, it shows us there are two versions now. Version 1, version 0. This is the original one, this is the new one. Here is the timestamp where it was changed. User ID who changed it, user name, operations, update. So here all the details are captured here very nicely, very useful for audit purpose. If somebody wants to see that, when the data was changed, why, if somebody is actually doing some investigation, then this is very useful. So then here we are giving the deletable path is this. We want to see what's the actual data in the current table. Then we are seeing that dot format delta load, and we are giving the path. And here we are giving one option, version as of 0. This is the original one. This is the latest one. And then we can see the data here. So mountain bike 3059. And here the price is a little bit less, 10%. So this is how we can see both the versions of the data. Then we can take temporary views on the data tables. Like we are creating a temporary view here. Then we can view it. We can write the select statements. Then we can also write using PySpark. If you don't want to write the SQL, you can write PySpark if you are more comfortable with Python. Then we can use Spark.SQL and then write the SQL inside. You can see the data. So, and if we are using the streaming data, and then we can use the here, for example, we are using the delta table as sink, and we are loading some trying to simulate the incoming data. So we are giving input path as the files / data. We are storing some data in here, and then we are defining the
Welcome back to the Deep Dive. If you are listening to this right now, I'm going to go out on a limb and guess where you are in life.
Oh, this is going to be good.
You are probably standing on the edge of a pretty massive career moment. Maybe you just wrapped up a grueling data science degree, or you've been grinding through certifications at night, and now you are staring down the barrel of the big one.
The technical interview.
To the technical interview.
And we aren't talking about the, tell me about your greatest weakness interview with HR. We are talking about the 1-hour, high-pressure, whiteboard-style grilling with an enterprise solution architect.
Exactly. The kind of interview where they stop asking if you know how to write a Python loop and start asking if you understand why your data architecture just cost the company $10,000 in storage fees over the weekend.
That is the shift, isn't it? It's the transition from I can write code to I can build systems.
Mm-hmm.
And specifically today, we are zeroing in on one of the hottest ecosystems in the enterprise right now.
Microsoft Fabric.
Microsoft Fabric, absolutely.
If you are looking for a data engineering role in 2025 or 2026, you're going to get asked about Fabric. You're going to get asked about OneLake. And you are definitely going to get asked about Delta tables.
It's the core.
It is the core. So the mission for this deep dive is, well, it's simple. We want you to walk into that interview and not just survive the questions, but absolutely crush them.
We need to move beyond the syntax. I mean, look, anyone can memorize a command. That's what cheat sheets are for. We need to understand the life cycle. We are going to break down the entire lifespan of a Delta table in Fabric from the moment you create it to how you ingest data, how you handle messy schema changes, and crucially, how you maintain it so it doesn't turn into a digital swamp 6 months down the line.
And to help us navigate this, I really want to give a massive, massive shout out to Rajan from the Tech Brothers IT channel. We're using a demo he put together as the backbone of our discussion today.
It's a fantastic demo.
It is incredibly comprehensive, and if you haven't seen his work, you absolutely need to go check it out. He didn't just show a hello world script. I mean, he built a real workflow.
That's what I loved about it. Rajan's demo covers the actual job.
Right.
He creates a lakehouse, attaches notebooks, executes PySpark, handles upserts with merge, and then runs the critical maintenance commands.
The ones people forget.
The ones people forget. Optimize and vacuum. That workflow from ingestion all the way to maintenance is exactly what architects are looking for in junior candidates. They want to know you see the whole picture, not just the fun little ingestion script at the beginning.
So let's get into it. Let's create the mental image. You're in the Microsoft Fabric interface. You've got your workspace open. The very first thing you do in the demo is create a lakehouse.
Right. And immediately, before we even write a single line of code, we have to talk about the storage format. It's a foundational choice.
Or is it a choice anymore?
That's the thing. In the old days, or even in generic Hadoop or Spark environments, you might have a debate, a big meeting. Do we use CSV? Do we use Avro? Do we use plain old Parquet?
Right, the pros and cons list.
Exactly. In Fabric, that debate is effectively over. The default, the native format, the one everything is optimized for, is Delta Lake.
Why is that?
Right.
Why is Fabric pushing us so hard toward Delta? What does it give us that, say, a folder full of Parquet files doesn't?
Reliability. I mean, it boils down to that one word. A lakehouse without Delta is just a file dump. It's a data swamp waiting to happen.
Okay, unpack that. A file dump.
Well, think about a raw CSV file. Let's say you have a Spark job writing 1 million rows to a CSV. The job fails at row 500,000. What do you have?
Half a file. A corrupted file.
You have a corrupted file, you have garbage. Delta Lake puts a transaction layer on top of those Parquet files. It brings ACID transactions, the kind of reliability you expect from a traditional SQL database, to your data lake.
So ACID's atomicity, consistency, isolation, durability. The classic database guarantees.
The very same. It ensures that either the entire 1 million row transaction is fully written and committed, or it isn't written at all. There's no in-between, no half-written files. That reliability is non-negotiable in an enterprise setting.
Okay, so we've created our lakehouse. We've accepted that Delta is our king. We open up the Explorer pane on the left, and we see 2 folders, just 2, files and tables. Now, to a beginner, this just looks like, some nice UI organization. Oh, I put my files here, my tables go there. But there is a massive architectural distinction here, isn't there?
There is, and this is where a lot of people trip up in interviews because it seems so simple on the surface.
It does.
The files section is, for all intents and purposes, unmanaged. It's the Wild West. You can drop a JPEG in there, a JSON file, a text file, a Python script, anything. Fabric doesn't really care what it is. It just stores it for you. It's a blob store.
It's basically a hard drive in the cloud. My personal junk drawer.
Exactly. It's your junk drawer. But the tables section, that's where the magic happens. Fabric has this really cool auto-discovery feature. If you drop a valid Delta table, which is really just a folder of Parquet files and a Delta log folder into that specific area,
It just finds it.
it just finds it. Fabric's background processes are constantly scanning that directory. They recognize the metadata, parse the schema from the transaction log, and automatically present it as a queryable table.
So you don't even have to write a create table script.
You don't. It just appears in the SQL endpoint. It appears for Power BI to use. It's a managed, curated space.
That is really convenient. But it leads us to a specific PySpark concept that I know burns people in interviews. We were looking at a Reddit thread about this. It comes up all the time. The difference between save as table and just save.
Oh, this is a classic. This is a top 5 interview question for a data engineering role using Spark. If an architect asks you, what is the difference between a managed table and an external table? Oh, this is exactly what they're asking about.
So let's break it down step by step. In Rajan's demo, he creates a data frame, and then he uses the command df.write.saveAsTable, my products table. What is actually happening under the hood when he runs that specific line?
When you run Save as Table, you are explicitly creating what we call a managed table. You are, in effect, handing the keys to the kingdom over to Fabric.
Handing over control.
Completely. You are saying, here is my data. You, Fabric, decide where it lives in the Managed Tables folder, you manage the metadata in the Hive metastore, and you own the entire life cycle of this data.
Okay, a managed sounds good. It sounds safe. I like having things managed for me.
Yeah.
But here's the scary part. The part that makes my palms sweat. What happens if I, a junior engineer, run a SQL command like drop table my products table?
This is the kicker. This is the gotcha. If you drop a managed table, Fabric says, okay, you want this gone, you gave me ownership, and now you're telling me to delete it. So it deletes the metadata from the catalog.
Of course.
And it physically deletes the underlying Parquet files from the storage layer. The data is gone.
Permanently.
Permanently gone. There's no undo button. You're heading to your backups if you have them.
That sounds terrifying.
Mm-hmm.
I mean, why would I ever want that? If I'm a data engineer, surely I want a safety net. Why shouldn't I just make everything an external table so I don't accidentally wipe out the company's entire sales history with a typo in a dia-drop statement?
And that is the instinctive reaction. And honestly, for many use cases, that's the right call. But think about it from a governance and compliance perspective.
Okay.
If you work in a regulated industry, healthcare, with HIPAA, finance, anything in Europe with GDPR, and you get a request to delete a user's data, a right to be forgotten request.
Oh, I see where you're going with this.
If you have external tables scattered all over your data lake and you run drop table, you might leave ghost data sitting in a folder somewhere that you forgot about. The metadata is gone, so you can't query it anymore, but the files are still there, the data still exists, and you are legally exposed.
Ah. So with a managed table, drop-E means drop. It's a guarantee of deletion.
Exactly. Managed tables ensure that when you say delete, you actually mean delete everything associated with this table. It's a trade-off. It's about governance and cleanliness versus that raw data safety net.
So save as stable is the strict compliance governance first option. What's the alternative then? The save command.
The alternative is using df.write.save, path to my data. For example, df.write.format, delta.save, files external products. This creates the delta files in a specific location that you define.
So I'm telling it exactly where to put the files. Maybe in that files junk drawer folder.
Precisely. And then you can register this location as a table in the metastore separately. This is what we call an external table. You're telling Fabric, hey, the metadata for this table belongs to you, but the actual data files, I'm managing those. They live over here.
And the big difference comes when you drop it.
Exactly. If you run drop table on an external table, Fabric only deletes the metadata pointer, the little entry in its catalog that says external products lives here.
But the actual Parquet files
Remain completely untouched on the disk. Your data is safe.
So managed equals Fabric owns the life cycle. External equals I own the life cycle.
That's the perfect summary. And in an interview, if you can articulate that trade-off governance versus control, cleanliness versus safety, you immediately sound much more senior than someone who just says one saves to a path and the other doesn't. You're showing you understand the architectural implications.
Got it. Okay, that's a huge one. Now, let's move to section 2. Writing data. We have established our table structure, managed or external. We've got our data frame. Maybe we read it from a CSV like in the demo. Now we are writing it out to Delta. We have the standard modes, overwrite and append.
Yeah, these are standard Spark fundamentals. Mode overwrite is the bulldozer. It comes in, wipes out everything that was in the table, and replaces it with the new data frame.
Looking for full refreshes of dimension tables, maybe.
Exactly. And mode append is the gentle approach. It just adds the new rows from your data frame to the bottom of the existing table without deleting anything.
Standard stuff. But in Fabric, there is a special sauce applied here. A performance feature that you absolutely need to know about for an interview. It's called V-order.
Ah, yes, V-order. This is one of those brownie point topics. If you can speak intelligently about V-order, the architect interviewing you will know you've done your homework on Fabric specifically, not just on general Spark.
Okay, hold on. You dropped a term there. V-order. It sounds like something from a Star Wars movie. Execute V-order 66. But in the documentation, it's listed as a write time optimization. Unpack that for me. When I write a file with V-order enabled, what is physically happening to that Parquet file that's different?
It does sound a bit sci-fi, doesn't it? To understand V-order, you have to first understand how a standard Parquet file is built. It's not just a flat text file like a CSV. It's a columnar format.
Right, it stores data by column, not by row.
Correct. And inside the file, the data is stored in chunks called row groups. And each row group has statistics, min value, max value for each column. So if you're looking for predicted equals 500, Spark can read the stats and say the max ID in this row group is 400, so I can skip reading this entire chunk of data. That's called predicate pushdown.
Okay, so Parquet is already pretty smart.
It is, but it's not perfect. Imagine you have data that's not sorted at all. Your IDs are all jumbled up. Even with the stats, Spark might still have to open and inspect a lot of those row groups.
Right. The min-max range for each chunk will be huge and overlapping.
Exactly. You're still doing a lot of searching. V-order takes this to another level. During the write process, it applies a very special sorting algorithm. It's related to things like Z-order curves, if you're into spatial geometry, that intelligently collocates related data within the file. It's not just a simple sort by one column. It's a multi-dimensional sort.
So it's organizing the file internally in a very clever way.
A very clever way, so that when the query engines in Fabric Power BI, the SQL engine, Spark itself, come to read it, they can eliminate massive amounts of data with extreme efficiency.
It's like building the most perfectly organized library imaginable. You don't just sort by author. You sort by author, genre, and publication, decade all at once. So finding a book is instantaneous.
That's a perfect analogy. You pay the tax up front, the time it takes to so perfectly organize the books on the shelf, so that every person coming in to read them later can find what they want almost instantly.
And the numbers on this are pretty wild. The sources say you can get up to 50% faster reads.
In some cases, yes. On average, it's more like 10–20%. But for certain query patterns, especially in Power BI, which uses a Microsoft technology called Vertiscan that is specifically tuned for this format, the gains can be massive. And you get better compression, too.
50% faster reads is a game changer for a dashboard. So this brings up the obvious question. Why isn't this just the default setting for everything? Why would I ever turn it off?
Because there is no free lunch. Ever. To get that incredible read speed, you pay a tax on the write speed. That complex sorting and organization takes computational power. Writing a file with V-order is about 15%, maybe 20% slower than just dumping the raw Parquet file.
Ah, I see. So if I have a real-time streaming job that needs to ingest data with the lowest possible latency, V-order might actually hurt me. It would slow down my writes.
Exactly. And this is a key insight. In fact, in new Fabric workspaces, V-order is actually disabled by default for Spark sessions.
Wait, it's off by default. That's surprising.
It is. Microsoft's thinking seems to be that if you are using Spark, you're likely doing heavy-duty data engineering, ingesting massive logs, transforming raw data, where write throughput is often the top priority. They prioritize getting the data into the lake quickly.
Whereas for Power BI or the SQL endpoint, read performance is king.
Precisely. And this is a crucial senior architect insight. If you are in an interview and you can articulate this trade-off, you're golden. You can say, well, for my gold layer tables that are directly consumed by Power BI dashboards, I would absolutely enable V-order using spark.sql.parquet.vorder.default is true. But for my bronze layer raw ingestion tables, I might leave it off to keep the ingestion pipeline as fast as possible.
And then maybe apply V-order later during a maintenance job.
We're getting ahead of ourselves, but yes, that's the advanced play. But just knowing when to use it and why it's not a magic bullet for every single table, that proves you understand the trade-off.
Okay, that's a huge point. So let's talk about when things go wrong. because they always do. Schema changes. This is the bane of every data engineer's existence. You build a beautiful pipeline, it expects 5 columns: ID, name, date, price, quantity. Today, the source file arrives, and it has a 6th column. Or the price column suddenly has dollar signs in it and is a string. In the sources we look at, Adrian Chertkowski had a great write-up on this, on schema enforcement versus evolution.
This is the daily reality of a data engineer. Things change upstream without notice. By default, Delta Lake uses what's called schema enforcement.
It's a strict bouncer at the door of your table.
Perfect analogy. It has a list of who's allowed in ID, name, date, price, quantity. If a new piece of data comes to the door with a comments column, the bouncer says, nope, you're not on the list, and throws an error. The write fails.
Which is incredibly annoying when you are testing and developing, but is probably a lifesaver in production.
It's a feature, not a bug. You should be grateful for it. It protects the integrity of your data. You don't want a pipeline to silently succeed, but start filling your clean, curated price column with string values like 1999s. That breaks every downstream dashboard and model.
Right. Data integrity first. But sometimes the schema change is valid. The business decided, we do need a comments column now. How do we handle that without the pipeline crashing at 3 a.m. and waking someone up?
That's where schema evolution comes in. It's the way you tell the bouncer, hey, it's cool, this new person is with me, let them in and add them to the list.
And how do you do that in the code?
In PySpark, when you do your write operation, you just add an option. An option, merge schema. True.
And that just tells Delta, hey, if you see a new column in the source data that's not in the target table, just add it.
Yes. If the source data frame has a new column called ordinal, or comments, Delta will automatically run an alter table command under the hood to add that column to the target table and then proceed with writing the data. It evolves the schema on the fly.
That sounds almost too convenient. Why wouldn't I just leave that on all the time? Just have a global setting, always merge schema, problem solve forever.
Oh, that is a very dangerous game. Adrian warns about this explicitly in his post, and he's right. Imagine a common scenario. You are ingesting a CSV that comes from a manual process. Maybe someone in the marketing department updates an Excel sheet every day and exports it.
I can already see where this is going. My anxiety is rising.
One day, that marketing person uses the spreadsheet for some scratchpad math on the side. They add a column called MyCalc V2, or lunch order, full of random numbers. They forget to delete it before they export and upload the file to your pipeline's landing zone.
And if merge schema is on,
Congratulations! Your production enterprise data warehouse now has a permanent column called lunch order. And since Delta retains history, it's not always a trivial thing to just undo that schema change cleanly. You have to be very deliberate about it. You've essentially polluted your data model.
right. So the rule is use it, but use it with extreme caution and ideally with some sort of validation step before it.
Precisely. Use it when you are intentionally and knowingly evolving the schema, not as a catch-all to prevent errors. It's also worth noting that Delta can handle some minor changes automatically without the flag. Like if a column was all nulls and you start putting strings in it, it will upgrade the null type to string type. Or if you upgrade a byte to an int. But for adding completely new columns, you need to make that conscious decision with merge schema.
Moving on, we've written data, we've managed the schema. Now let's talk about updating the data that's already there. In the demo, Rajan showed the basic deltatable.update and deltatable.delete methods.
Yeah, those are great commands for ad hoc fixes. A DBA might use them. Oh, we need to update this specific user's email address or delete this one fraudulent transaction. You give it a condition and it does the work.
But for big data pipelines, we rarely run row-by-row updates like that. We're usually dealing with batches of changes. A new file arrives with 10,000 updates.
Correct. And that leads us to the most powerful, most common, and arguably most important DML command in the data engineer's arsenal, the merge statement.
The upsert, the classic ETL pattern. If it exists, update it. If it doesn't, insert it.
Exactly. It's the holy grail of data warehousing. The logic is simple. You have a target table, your main Delta table, and a source, your new batch of data. You tell Delta how to match them, usually on a primary key, like source.customer, target.customer.
And then you define the rules.
Right. You say when matched, then update to update the existing records. And when not matched, then insert to add the brand new customers who weren't in your table before. You can even add a when not matched by source, then delete clause for things like slowly changing dimensions. It handles all that complex logic in one single atomic operation.
The syntax can be a little verbose in PySpark, a little more complex than a simple write.
It is. You have to define the Delta table object alias the tables, define the condition, and then chain your clauses. When matched, update all, and when not matched, insert all. But the power it gives you is immense.
But here's where we get into another Fabric special again, another performance optimization. The sources mention something called low shuffle merge.
Yes, this is another one of those key Fabric-specific features to bring up in an interview.
Okay, we need to pause on this low shuffle thing because that sounds important. You mentioned earlier that shuffling is the #1 performance killer in Spark.
Why?
What is physically happening in the cluster when Spark shuffles data?
Okay, let's use an analogy. Imagine you have a deck of playing cards, but the cards are not in one pile. They're spread out across 50 different tables in a giant warehouse. Each table is an executor, a worker machine in your Spark cluster.
Okay, I'm visualizing it. 50 tables, cards scattered everywhere.
Now I give you a simple task. Put all the aces together on one table. The ace of spades is on table 1. The ace of hearts is on table 27. The ace of clubs is on table 42. What do you have to do?
I have to physically walk to each table, pick up the ace, and carry it across the warehouse to a designated ace table.
That's a lot of running around.
A lot of running.
That running back and forth across the warehouse floor, that is shuffling in Spark. It's network traffic. It's moving data between the physical machines. It's taking the data, serializing it, sending it over the wire, deserializing it on the other side. It is by far the slowest and most expensive thing a distributed system can do.
So when we do a standard merge, say in open source Delta Lake,
In a standard open source Delta merge, to figure out which source rows match which target rows, Spark often has to shuffle a huge amount of data. It might have to move all the data to be co-located on the same machines based on the join key. It's running back and forth with a ton of cards it doesn't even need to touch just to perform the comparison.
it's inefficient. It's shuffling cards that aren't even aces, just in case.
Precisely. And Fabric's low shuffle merge optimization is incredibly smart about this. It's like giving everyone in the warehouse a walkie-talkie.
Okay.
The system is a preliminary check. It looks at the data on table 1 and table 2 and says, hey, I can see from your stats that you don't have any matching customer IDs. Stay put. Don't move your data. It effectively filters out the rows that are not going to be modified before the shuffle phase.
So it only moves the specific data, the specific cards that actually need to be updated or inserted.
Exactly. It dramatically reduces the amount of data sent over the network, which means the merge operation is faster and uses fewer compute resources.
Which explains why some of the performance benchmarks for merge in Fabric are so much better than in standard Spark.
Correct. And it is enabled by default in Fabric. The config is spark.microsoft.delta.merge.lowshuffle.enabled. You don't have to do anything to get this benefit, but mentioning it in an interview shows you aren't just thinking about the logical query, you're thinking about the physical execution plan. You're thinking about efficiency and cost.
Okay, let's talk about the oops button, the safety net. We've all been there. You run a delete command, and a split second after you hit enter, you realize you forgot the where clause.
The cold sweat moment.
You just deleted all the data for the entire UK region instead of just for one customer. In a traditional database, you are frantically calling the backup and restore team and sweating bullets. In Delta Lake,
In Delta Lake, you take a deep breath and you just use time travel.
this sounds like magic, but it's actually just really clever logging, right?
It is. It's all because of that Delta log folder we mentioned earlier. Every single time you write, update, merge, or delete data, Delta doesn't actually overwrite the old data. It operates on a principle called copy on write.
Copy on write. Explain that.
When you update a row in a Parquet file, Delta doesn't go into that file and change the text. That would be slow and dangerous. Instead, it reads the relevant data, makes the change in memory, and writes out a brand new Parquet file with the updated data.
Okay, so now I have two files, the old one and the new one.
Correct. Then it goes to the Delta log and creates a new JSON file, a new transaction entry. This entry says, for the current version of the table, stop reading the old file and start reading this new file instead. The old file is now considered outdated.
So the old file is still sitting there on the disk. It's not deleted.
It is sitting right there, physically untouched. It's just no longer part of the active version of the table.
So in the demo, Ragin uses the command, describe history myficable. What does that show us?
Right. That command reads the transaction log and shows you the full timeline of your table. It'll say, version 0, create table. Version 1, write, appended 1,000 rows. Version 2, merge, updated 50 rows, inserted 10. You can see who ran the command, what time they ran it, and what operation they performed. It's a complete audit trail.
And if I want to see the data as it was before my terrible delete mistake at version 3,
It's as simple as reading the data frame with a special option. Spark.read.format, delta.option, version ASOF, 2.load, path potable. You're literally telling Spark, ignore the latest version, show me the state of the world at version 2.
And you could even take that data and overwrite the main table to roll it back.
You could, or you can use the restore command, which does that for you. Restore table, my table to version as of 2. It's a powerful disaster recovery tool.
This is vital for debugging too, right? You get a business user saying, why did the quarterly report look like this yesterday, but it looks different today? Well, let's go back to yesterday's version and check the data.
Exactly. It's an audit trail and a disaster recovery tool all in one. It provides reproducibility, which is huge for data science as well.
But this leads to a problem, a big, expensive problem. If we are keeping every version of every file forever, and we are doing all these appends and merges and creating new files constantly, aren't we going to end up with a massive, messy, and very expensive collection of files?
We are, and this leads us to the final and perhaps most important section, optimization and maintenance. This is where the junior engineer becomes the senior architect. This is where you prove you can maintain a system for the long haul, not just build it once.
I want to role play a scenario here.
Yeah.
I'm a junior dev. I built this beautiful new streaming pipeline. I tested it with a 1 GB CSV file. It ran in 30 seconds. I pushed it to production. My boss is happy. Everyone is happy.
I know exactly where this is going. The calm before the storm.
3 months later, the CFO calls me. The Power BI dashboard that used to load in 5 seconds now takes 5 minutes to refresh. The cluster costs for querying this table have tripled, but the actual volume of data, the number of rows, hasn't changed that much. What did I do wrong?
You, my friend, have fallen into the small file trap. This is the silent killer of data lakes.
Diagnose it for me. What happened?
Your streaming job, or maybe it was a microbatch job, was probably running every 10 minutes. And every time it ran, it wrote a new batch of data. And every time it did that, Delta created a new file, a tiny 10 kilobyte Parquet file.
So after 3 months,
After 3 months, you don't have one big, efficient 1 GB file. You have 500,000 tiny little files.
and Spark doesn't like that.
Spark hates it. The query planner has to list all 500,000 files from the storage system. That alone takes time. Then, for each tiny file, I have to open the file, read the metadata footer, process a tiny bit of data, and close the file. The overhead of just managing the files takes way longer than reading the actual data inside them.
It's like trying to move a house by carrying it one brick at a time instead of using a truck.
Perfect analogy. The overhead kills your performance.
So what is the fix? How do I get out of this mess?
The fix is a simple, beautiful command called optimize. You run optimize your editable name.
And what does that do physically to the files on disk?
It performs an operation called bin compaction. It's like a data janitor. It goes into the folder, grabs all those tiny 10 KB files, reads them all into memory in a Spark job, and then rewrites them as a small number of large, perfectly sized files, usually around 1 GB by default. It consolidates all the bricks into a few big, solid walls.
And performance is instantly better.
Instantly. Your queries will fly because Spark now only has to open 1 or 2 files instead of 500,000.
And here is the connection back to vOrder, right? This is the aha moment for me, connecting these two concepts.
Yes. This is the professional workflow. This is what you draw on the whiteboard. Remember we said vOrder slows down, right? A very common and effective architectural pattern is this. Let your daily streaming or microbatch ingestion run fast without vOrder. Just get the data into the lake as quickly as possible, creating those small files.
Okay, so the data is in, but it's messy.
It's messy, but it's there. Then, once a night or once an hour, you run a scheduled notebook that executes the optimize command.
And that optimize command does 2 things at once.
It does 2 beautiful things at once in Fabric. It compacts the small files into big ones to solve the small file problem, and it applies the vOrder sorting at the same time. So your users get lightning-fast Power BI reads the next morning, but your real-time ingestion wasn't slowed down during the day.
That is a brilliant workflow. Write fast, read fast. You get the best of both worlds by separating the operations.
That is the kind of thing that gets you hired. It shows you're thinking about the entire system, the trade-offs, and the user experience.
Now, what about the other problem we identified? The storage cost. Time travel is great, but do I really need to keep the version of the table from 3 years ago from every single microbatch?
Probably not. And you are paying for that storage. Every one of those old Parquet files that's no longer part of the active table state is still sitting there, costing you money on your cloud bill. This is where VACUM comes in.
The janitor of the Lakehouse comes back to sweep the floors.
Exactly. You run VACUM, your label name, This command looks at the transaction log, finds all the data files that are no longer referenced by the latest state of the table and are older than a certain retention threshold.
And what's the default threshold?
The default is 7 days, and any file that meets those criteria gets physically and permanently deleted.
Poof. Gone. So it cleans up your storage and saves you money.
It does. But there's a massive catch here, a point of no return. You have to be careful. The catch is, once you vacuum, you have burned your history books. You can no longer time travel back to those versions because the physical files they depended on are gone. If you vacuum everything older than 7 days, and then you realize you need to see the state of the data from 8 days ago.
Tough luck.
Tough luck. The log entry is there, but the data files aren't.
So the cardinal rule is never run VACUM with a retention of 0 hours unless you are absolutely 100% sure you know what you are doing.
Correct. By default, Spark has a safety check to prevent you from doing that. You have to disable a setting to even allow it. It's a protection against shooting yourself in the foot because you lose all your safety nets.
There's one more optimization technique mentioned in Adrian's blog that we absolutely have to touch on because it's a classic interview topic: partitioning.
Right. Using partition by when you write your data. This is about physically organizing your data into subfolders based on the values in a column, like year or month or country.
So physically, on one lake, you'd actually see a folder for year 2024. And inside that, a folder for month January and so on.
Exactly. And the massive benefit you get from this is an optimization called partition pruning.
Pruning?
If you run a query like select from sales where year 2025, Spark is smart enough to know it doesn't even need to look inside the 2023 or 2024 folders. It prunes them, it completely skips them, and only reads the files in the 2025 folder. It can save massive amounts of I/O on large tables.
You can even prove this is happening, right?
You can. You go to the Spark UI, look at the query plan, and you'll see a metric like number of files read. If you run it with the filter, you'll see it read far fewer files than without it. It's tangible proof.
But Adrian had a big warning here too. A classic beginner mistake. Do not over-partition.
Yes. This connects directly back to our old enemy, the small file problem. Imagine you have a relatively small table, say 500 millibits of data for the whole year, and you decide to get clever and partition it by transaction merit.
You're creating 365 folders.
And each folder is going to have, maybe 1 or 2 megabytes of data in it. You have just artificially created the small file problem for yourself. Your performance will get worse, not better.
So what's the rule of thumb for when to partition?
Don't partition unless your table is large. We are talking many gigabytes or terabytes. And the partition key should be low cardinality, meaning it has a small number of distinct values. A good rule is that each individual partition should contain at least a gigabyte of data. If your data is small, just let it be unpartitioned. Modern alternatives like liquid clustering are emerging to solve this, but partitioning is still the standard interview topic you absolutely need to know inside and out.
Okay, before we wrap up and bring this all home, we should briefly mention streaming. The demo touched on it, and it's a huge part of the modern data stack.
Right. We don't need to go too deep here, but you should absolutely know that Delta tables are built for streaming from the ground up. A Delta table can be both a sink, a destination for a stream, and a source, something you can read from as a stream.
So you can use read stream and write stream directly on a Delta table.
You can. And because of the ACID compliance and transaction log, it's incredibly robust. You can have a Spark structured streaming job pouring data into a table in near real time, while your Power BI dashboard is reading from that same table, and it won't crash or show corrupted data. It allows for a true near real-time analytics layer in the Lakehouse.
Incredible. Wow. We've covered the creation, the storage choices, the writing with V-order optimization, schema evolution, the powerful merge strategies, the safety of time travel, and the crucial maintenance with optimize and vacuum and partitioning.
That is the full stack. That is the entire life cycle of a Delta table.
So let's bring it all together. You are sitting in that interview chair, your palms are a little sweaty, the enterprise architect leans forward and says, okay, walk me through how you would design a robust and efficient Delta table architecture in Microsoft Fabric. What are the 5 key pillars, the talking points you absolutely need to hit in your answer?
Number 1, storage. You start by saying Delta is the default format for reliability. Then you immediately explain the difference between managed tables using save as stable for strong governance and external tables using save for more control and data safety.
Check.
Number 2, ingestion. You discuss schema. You mentioned that by default, Delta enforces schema, which is good, but you know about schema evolution with merge schema, and you'd use it cautiously to avoid polluting your data model with bad columns.
Good.
Number 3, operations. You say that for incremental updates, merge is your daily driver. And you specifically mentioned that Fabric optimizes this with low shuffle merge to reduce network traffic and save compute costs. That's a huge bonus point.
Love it.
Number 4, optimization. This is the big one. You explain the write fast, read fast pattern. Ingest data quickly without vOrder, then run a scheduled, optimized job at night to both compact the small files and apply vOrder for the reporting layer. You also mentioned partitioning for large tables, but you're aware of the dangers of over-partitioning. And finally, number 5, safety and cost management. You explain that time travel is your built-in safety net for debugging and disaster recovery. And to manage the storage costs of that history, you would implement a VACUM job with a sensible retention period, like 7 or 30 days, to clean up old files.
If you can weave those 5 points into a coherent narrative about a data pipeline you built or, practiced with using Regions demo, you are going to sound like you've been doing this for years.
Absolutely. You are no longer just a coder. You are speaking the language of an architect. You're talking about trade-offs.
And I want to leave the listener with one final provocative thought, building on that idea of trade-offs. We talked a lot about defaults today. Low shuffle merge is on by default. vOrder is off by default for Spark.
That's right. And I think that's the ultimate test of a true architect. Microsoft gives you the switch. They give you the configuration knob. They don't force a single path on you. The architect decision is knowing when to flip that switch.
It's the why.
It's the why. Is your workload write-heavy and latency sensitive? Keep vOrder off. Is it a read-heavy reporting table for the CEO? Turn it on. Is your data source messy and unpredictable? Keep merge schema off and let it fail loudly. Is it a well-governed source that's rapidly evolving? Maybe you turn merge schema on.
It's not about knowing the command. It's about knowing the consequence of the command.
Exactly. If you can explain why you made that configuration choice, you demonstrate that you understand the fundamental trade-offs of the entire Fabric ecosystem. And that, more than anything, is what gets you hired.
Trade-offs. That's the name of the game. A huge thank you again to Rajan at Tech Brothers IT for the incredible demo that powered this entire discussion. And thank you to Adrian Tchaikovsky for the deep dive blogs that added so much color.
And thank you to you, the listener, for investing this time in your career.
Now, don't just listen. Go open a Fabric notebook, fire up a trial, run the code, create a table, append to it, merge it, and then break it. Purposely delete something you shouldn't, then fix it with time travel. That's how you really learn this. We'll see you in the next deep dive.
Happy coding.